Assume I'm recording, even though I can't see it. So let me see if I can spot where I am. And there it is. Let's get that full screen. I think I'm recording. All right. So this is a little thought exercise. I want you to sketch what you get when you multiply those two graphs together. I intentionally not written any numbers and certainly haven't labeled anything. So pause the video and try to stay in that mindset. Graph those two videos. It's early morning here. Graph those two. What do you get when you graph the multiplication of those two functions? One is g of x, one is f of x, and try to work with just the graphs. So you're pausing the video. I'm going to start chat. Oh, so what does it mean to multiply a couple of functions together graphically here? Well, one thing I can tell you is numbers are either positive or negative or zero, right? And they have either large size or they're small. And we don't have any numbers on these graphs at the moment, but one thing I can tell you is that g of x over here is positive, right? These are positive values and these are negative values, and they're eventually getting big. And so if I multiply a positive and a negative and they're both big numbers, then I guess I get a big negative number. And so therefore, as these get bigger and bigger and bigger, my negative numbers are getting bigger and bigger and bigger. So it's going down over here. And let me state that again. So we have y, which is a function of x, right? We're doing some calculation, and that's one of the graphs. And then we have another one, right? G of x, another calculation based on x. And if we multiply that times that, it's implying that we're multiplying these two y values. Okay, so that's what I'm doing. And over here, the same thing's happening. I've got a significantly large negative number. This is going to negative infinity. This is going to positive at different rates, of course. Going, to infinity and negative infinity at different rates, but big negative, big positive, it's going down. And there's something else I can tell you. That it's crossing the x-axis, the y values are zero. And 0 times anything is 0. So I know my graph goes through here, and I know it goes through here. And now I have two y values, negative and negative times a negative is a positive. This thing has got to max out somewhere. It's got to max out somewhere. And intuitively, probably between the roots, which means that we're going to get a graph, and I'll do a dotted line now. Boom, 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 and there's your parabola. And if we take a little deeper dive into this, and then name the functions that I gave you, we got a lot of little dots here and everything else. It's rotator cuff problems drawing this. It turns out it maxes right where I drew it. If I got Desmos out right now, that would be pretty accurate. And that's a negative y value, right, to where it intersects here. And this is a negative y value. And that negative times that negative is giving us our max. Now, let me tell you what the linear functions were. This one was minus x minus 2. And this one was 3x minus 6. Okay, now we're going to get back into some analytics here. And if we multiply those two things together, we actually get 3x minus 6 times, see, minus x minus 2. It's early here. I don't want to have to do much thinking because I'll do something careless. So that's minus 3x squared. I'll do this for you quickly. Minus 6x plus 6x. Right, negative times negative minus 12. Right, obviously those cancel. So we get 3x squared minus 3x squared minus 12, plus 12, excuse me. And so that's obviously our vertex is at 0, 12 here. I think we can see it, right? But back to the average of the roots. Okay, and the average of the roots we've looked at, in the other videos extensively. is minus b over 2a. And minus b in this case is 0, right? In the ax squared plus bx plus c. All right, so stands to reason that that's where the vertex would be. But a deeper dive allows us to look at this from a factorial situation. I could have factored out the 3, and that would have given me x minus 2. And then this one is still minus x minus 2. All right. And it turns out that if you put a 0 in here, this is minus 2 units. And if you put a 0 in for the first factor, this is minus 6. And if you divide that by 3, you get minus 2. Which means that I've got a little squaring process going on. And I'm not quite sure how to describe this. But if you were to complete the square, right? And in this one, we basically did when I wrote 3x squared plus 12, but I could have written it as 3 times x minus 0 squared plus 12, right? There's your HK form, all right? There's still this completing the square process that's taking place graphically as well, and that has to be true, right? So, again, I'm not quite sure. I'm just beginning to think about this a little bit more deeply from a graphical perspective. So I don't have the language yet that I want to have, but with enough repetition and I keep looking at it, hopefully we'll smooth that out. But there's the completing the square process taking place here right before our eyes. Okay. All right. Not quite sure what I'm talking about, but I just wanted to get you thinking about what it means to add a couple of graphs together and to multiply graphs together. Might help your graphic skills, all right? Especially when you start looking at composites, okay? And what you're looking at is, if you're adding graphs together, you're adding the y values. If you're multiplying graphs together, you're multiplying the y values. And also, the rates of change that go with them. That's very helpful. I really should stop this video, start another one, and dive into that, because that is the key to understanding cubics in graphing form and quadratics in graphing form. Okay, so think about the rates of change that are occurring. So this maxed out. So why have one function going down and another function going up at a different rate? You know, if I factor out the 3, then this is a 1-to-1 going up, and this is a 1-to-1 going down. And if you add those rates together, you get a 0 for a rate, which is really heading us towards some calculus concepts for finding local maxes and local mins. So I knew there was something there that I wanted to say, and I finally got it out. All right, and at least I'm going to post this and, you know, hopefully maybe do this video again when I have a clearer explanation. But I'm getting up there in age, so I thought I'd do it. All right, now where's my cursor? Oh God, I wish I could see better. There it is. Stop the video. Have a good day.